So now let's talk about complex numbers for a minute. As if complex numbers weren't difficult enough, what with their being unreal and all, we're used to having them in a plus bi form, where a and b are real numbers and I is imaginary. And we have in the past graphed them on a rectangular plane where the x-axis is the real axis and the y-axis is the imaginary axis. Now, just to make things more interesting, let's take polar coordinates and throw complex numbers into them. What does that mean? It means that you're going to have complex numbers that look like a plus bi, and they are going to change. A is x, b is y. A is r cosine theta, b is r sine theta. And r squared is still a squared plus b squared. Because the a and the b in the imaginary number, or the complex number, represent, in the graphing that we do, the x and y coordinates. So if you're going to change them into polar form, this is how you do it. This is what it looks like. And this book takes cosine theta plus sine theta and shrinks it so that you have less writing to do. R cis theta means r times the quantity cosine theta plus I sine theta. R is called the modulus, theta is called the argument. But here's where it starts to get more interesting. You can multiply complex numbers more easily in this form than in the other form. If you have it in this form, you can multiply two complex numbers together by multiplying the moduli and adding the arguments. And you divide by doing the opposite. Divide the moduli, subtract the arguments. And then reciprocals, it means you take the reciprocal of the modulus and the opposite of the argument. And then you have de Moivre's theorem. All you do is raise the modulus to the power, multiply the argument by the power. And that means you can find roots, you can find powers.
So for the modulus is r, so then you would do the cube root if it was...
Yeah, a cube root is raising to the 1/3 power.
Right, so but then the argument would just be dividing by 3, in this example.